Right, this is continues of the ratios and the root test. Um, Now, here is the last test that we will need to learn the test whether a series is convergent or divergent. The series here, the test here will relies on the nth root. Okay, so that's what I call the root test. So basically, we take the nth root of the general term, take nth root of general terms, and if the limits equal to say L, and if that limits L less than 1, then the series converges absolutely. Notice that when we apply the root test here, we take the absolute values of the term. So that's why when it converges absolutely. If it's bigger than 1, the series diverges. If it's equal to 1, then the test is inconclusive. Know that these three conclusions here is the same rules for the ratio test. If you recall up here, when we do the ratio test of consecutive terms equal to L, see these three conclusions or here will be the same as these three. Okay. Now, why do we use this test? Notice that we take the root, the end root of the term. So basically, the end root will simplify or help simplify the formula when you have the n powers, right? If you get a square root of x squared, it's x. The cube root of x cubed is x. So it works really well when you have a series that could be written as an n power of the entire terms. Okay, so I'm going to do an example about that. You can see whenever you have something raised to n power, the root test will be used. Again, it will be very easy to recognize. And the second remark here, if the ratio test fails, okay, remember the ratio test fails when the limit L equals 1. If the ratio test fails, do not try root test because your L will be 1 again, and therefore it's inconclusive. Okay, let's take a quick look here. Test the following series. Find n minus 2nq over nq plus 4n squared quantity raised to the n power. Do you see that it's raised to the n power? So when you see that happens, you know that we're going to use the root test. And in fact, it makes things a lot easier to do if you apply the root test. Again, because the n power here, that kind of make it hard to determine whether the series converge. But if I apply the root test in this case, I'm gonna do limit, okay, the n root of the absolute values of a sub n and approach infinity. Right, so that is the problem number 1 here. Now, what it means is I take the n root of this quantity. So what do you think if you have the n root of this? Right, the n root and the n power got canceled out. And so you would end up with, actually I have absolute values. So it will become just an absolute values of, I still need the limit. Okay, so I have the limit of absolute values of phi n minus 2nq over nq plus 4n squared, absolute values. Again, taking the n root of the n power, cancel out, you're left with this, and I can find the limit easily in this case using our shortcut. You see that the numerator has degree 3, the denominator has degree 3, so they have the same degree. It will be leading coefficients over the leading coefficient here is 1. So I guess the limits here is negative 2 over 1. But don't forget that it's inside the absolute values, and therefore the limit is 2, positive 2. And because the limit is 2 bigger than 1, we can conclude the series we are testing, the series converges by the root test. Okay, right, so that's pretty easy to use. Look at number 2. For number 2, the same thing. Well, it doesn't look like the root test at first because you don't have the whole thing raised to n power. However, this series can be easily written as, you see the top raised to the n, denominator raised to the n. So that's equivalent to negative 1 over natural log of n, quantity raised to the n power, and from 1 to infinity. Okay, so what we do is, again, take the limit of the n root of a sub n in absolute values and approach infinity. So what does it do? It will remove the n powers. Okay, it removed the n power, and that becomes just negative 1 over natural log of n in the absolute values. Well, what's this limit? As n's increase, fraction decrease, that approach 0. Right, so now it's less than it approach 0 and it's smaller than 1, so we can conclude the series diverges in this case. Okay, again, by root test. Now notice that we have many tests, so each time we conclude the series converge diverge, be sure to name the test. Which one are we using? Based on what test or what type of series. All right, so that basically finished the section. We have several quantity, several sections actually from 9.2 through 9.6 with 10 different tasks actually. So let me do a quick summary here, and I have a table here for you to reference, so we can so we can determine quickly which one, which test to use. All right, so here's a strategy for testing series in general. We have, let's see how many. See, test for divergence, geometric series, P series, alternating series, telescoping series, root test, ratio test, limit comparison, direct comparison, and integral test. We have a total of 10 of them. Now, I list them in the order that you should try first. For example, the test for divergence is the one that you should try first, because it's easy. So what you do is take the limit of the general terms a sub n and approach infinity. If that's not 0 or doesn't exist, then that series here diverge. Okay, so that only tells whether it diverged, and it's never conclude its convergence. Okay, so it's inconclusive if the limit is not, if the limit equals 0. Okay, and then the next things, next in the table, we have 1, 2, 3, 4. So this is a 4 special type of series. Okay, this with the special names. And geometric series is the one that has the form a times r to the n, or maybe to the n minus 1. Remember that one? So you have to figure out a common ratio If the common ratio in absolute value is smaller than 1, series converges. Bigger than or equal to 1, it diverges. And notice that when it converges, the sum will be a over 1 minus r. A is the first term, r is the common ratio. Then we have a p series. A p series is 1 over n to the p. Okay, p bigger than 1, it converges, and if it's less than or equal to 1, and of course it has to be positive component exponent. It's less than or equal to 1, it diverges. Then we do have a alternating series. That one has a negative 1 components, 2 raised to the n minus 1 power times the b sub n. B sub n is a positive term, right? So remember, if you have that alternating series, you check two conditions. A sub take the limit, b sub n approach infinity. If that's equal to 0, and if b sub n plus 1 less than or equal to b sub n, or the sequence decreasing, then the series converges. Okay, we can ignore, remember he did not cover that. And the next one is the telescoping series, right? Telescoping series is going to be the one we do partial fractions split into the form b sub n minus b sub n plus 1. Okay, so that one we use the definitions. Now the next two is the root test and ratio test. On the left-hand columns, I have the clues. So these are very important. You need to check to see. That will give you the kind of quick clue of which test to use. Now we have 10 of them, and you might be confusing which one we're going to use. Okay, so looking at the clue. The root test, the clues, it's easy. Whenever you can write the series as b sub n to n power, something raised to n power, then you're going to use root test. Remember that something has to be the entire term. Like, see this one, the entire term to n power, the entire term to the n power. Okay, so if you have a series where it just like limit of 3 to the n time n squared over 7 to the n, say. Okay, so not limit, series. So let's say you have a series like this. Okay. Then notice that this has an n power, but it's not the root test because you cannot write that as something to the n power for the entire term. Okay, that's n power, but it's the second power. So that is not the root test. Next, we're going to use the ratio test. Ratio test, this is the one where the series will involve factorials, powers, and exponentials. Right, so it looks like the series, this example over here will be the ratio test because we have what? We have this is the exponential 3 to the n, this is exponential 3 to the n, this is the power n squared. So when you have the power, the exponentials, especially factorial, if you ever see the n factorials there, then the ratio test will be almost guaranteed work. Okay, so we're going to use the ratio test. And then the next three, we have the limit comparison test. That works well when we have the series involve rational functions. So by rational functions, I mean the one that look like n cubed minus 5n squared over 4n to the third plus 7n plus 8n to the fifth. So again, just write some random examples. This is a polynomial in third degree, it's a polynomial fifth degree. So we have the rational like this. The ratio, the limit comparison test will be used. Okay. Now remember, for the limit comparison test, you have to come up with a test, a series. The b sub n is the one that you need to come up with. before you do the limit of the ratio. Okay, take the limit of the ratio. But then, how do you come with the B sub n? Well, the quick trick I show you is, again, take the leading term. Basically, this is insignificant. These three terms, third, first, this is the fifth. So that one is really the dominant, leading terms here. So you kind of drop these two, you take just the NQ over the 8 n to the 5th. When you simplify, that's really 1 over 8 n squared. And that is your B sub n as you're trying to do the C testing a series. Okay. So that's the comparison. And then the direct comparison is pretty similar in the sense that you have to come up with a test to do. Come up with a series to compare using the same strategies that I do have here. And also, don't forget that when you see the sine, the cosine, those functions usually are the clue that we're going to use the direct comparison test. And finally, the integral test is the one that is harder to apply. So you have to find three conditions, find a function, satisfy three conditions. And so that is the last test you're going to use if all other tests fails, right? Right, so you can try to do some more example and using this table to see if you can know which test to apply.